a new clean renewable energy generator and a new energy amplifier to be produced in this video. A technology to generate high energy look on all time with long life with finite size and can replace dangerous energy sources like dams and other inefficient sources that have short life and expensive costs with spoiling to nature and take large spaces. In this video, this first efficient energy amplifier and power generator to be shown. Note: this technology is protected by a copyright and for any information contact oblivion.238.53.32@gmail.com. Facebook, Actum Growth. Introduction. This new technology produces abundant, clean, renewable energy that lasts all day. It is inexpensive, easy to implement, and practical. The technology utilizes a new technique to generate very high energy. Blocks representing the generator are raised to a certain height, consuming minimal energy in a short time. These blocks, once raised, travel down a long, inclined line, which may take a considerable amount of time to reach the bottom. During this time, energy is generated through induction. Each block, representing a magnet mounted on a car, passes under a coil fixed to the track and then under other coils until the end of the long track. The cars are connected to each other like a train, with 63 cars per train. The train controls its speed when descending and ascending the track. At the end of the track, the path inclines to the beginning of an opposite track with the same configuration. The trains ascend from a point directly opposite the second track at the end of the inclined path, which begins at the end of the first track. At the end of the inclined path, a straight track ascends at a 63-degree angle to the beginning of the second, opposite track, which has the same configuration as the first. The train then rotates between the two tracks. It generates energy continuously, producing a very high output of 23.8 gigawatts for $95 million in construction costs. Depending on the energy harvesting technology, this cost can be reduced to $63 million for 63 gigawatts. This energy is produced continuously throughout the day, and the project can be built in a short time, perhaps no more than 63 days, at this cost. This clean, high-energy technology could potentially achieve net zero emissions in just 63 days. This project is compact, with a length of 630 meters for the small generator, which has a capacity of 23.8 gigawatts and boasts an aesthetically pleasing design. Technology explanation. A brief introduction to the system. The generator, a magnet mounted on a wheel weighing 63 kilograms, is lifted to a height of 6.3 m and consumes 3,200 watts of power in a short time. This magnet then moves down an inclined slope of 630 m or 6.3 kilometers, at an initial speed of 6.3 meters per second, reaching a speed of 63 meters per second. This speed can be increased on longer tracks to generate more power. At this speed, the wheel will take a long time to reach the end of the track. The car carrying the magnet then descends the inclined track, passing under coils spaced apart along the length of the track. Each time the magnet passes under a coil, it generates electrical energy through induction, producing very high power. A group of cars is connected to this car to form a train. Each train consists of 63 cars connected to a leading car that controls the flow. The train moves in a regular pattern, generating electricity as it travels downhill. At the end of the track, it ascends to an opposite track, which is identical in structure but runs in the opposite direction. The end of the first track marks the beginning of the second, where the train ascends again to the second track. Conversely, the first track begins at the end of the second. The process is repeated continuously, with multiple trains connected along the long track to generate continuous power. Each inclined track contains 63 parallel lanes. The total power generated by the two tracks and their 63 lanes is 2.38 gigawatts, GW, on the shorter track, which is 6.3 meters high and 630 meters long, operating at a speed of 6.3 meters per second. Increasing the speed tenfold, the initial speed generates 10 times the power, resulting in 23.8 gigawatts. Further lengthening the track produces 63 gigawatts. Detailed explanation of the technology: a 63 kilograms mass, represented by a magnet mounted on a car, is lifted to a height of 6.3 meters, consuming 3,200 watts of power. This power is used for each car involved in lifting the mass. The car is accelerated from an initial speed of 6.3 meters per second to 63 meters per second. The speeds depend on the system's length and stability, potentially reaching 630 meters per second or 6,300 meters per second. These are advanced figures requiring sophisticated systems and control mechanisms to manage the movement and generate very high power. The magnet consists of a magnetic disc mounted on a carriage with a diameter of 28 centimeters. The number of turns of the coil carried above the magnet on the track is 63, and the carriage speed is 6.3 meters per second. The following calculations determine the electrical energy produced by the magnet's movement near the coil and the coils carried on the track. Note the power is 15.4 kilowatts, and the total power is represented by the power of the cars that fill the track. The number of cars is equal to the number of turns on the track. Since each track contains 63 turns, the total power resulting from two parallel and symmetrical tracks is. Note that the power reaches 2.38 gigawatts for the simple system. This power is increased by increasing the path length by 5 times or so and increasing the speed by 10 times. A slightly longer and faster system produces approximately 63 gigawatts of power. The power output increases with increasing speed. At dB dt 10 times faster, V is 10 times more, and then the power is P is about 23.8 gigawatts. This energy is enough for 17 million homes and a city of 95 million people. Regarding the system cost, it is calculated as follows. When the number of turns is 63 per coil, and the total number of turns is fixed in the overall system, the length of each coil is less than 1 meter with a radius of 28 centimeters, and its weight is 0.1 kilograms of copper for a 63 amp current wire of 10 AWG gauge. If the price of 1 kilogram of copper is approximately $10, and adding the cost of magnets, which are certainly cheaper for construction, and then the cost of steam-powered generators, the cost of generators to produce 1 gigawatt of power is $10 million, as generating 400 megawatts costs $3 million, while generators producing 1 gigawatt reach $10 million, then the final cost for a small system, represented by a height of 6.3 meters and a length of 630 meters for two parallel systems, with a production capacity of 23.8 gigawatts, is calculated as follows. Cost equals number of turns * number of coils * number of parallel ways * number of systems plus extra number for magnets plus cost of steam generators. Cost is equals 63 * 1260 * 63 * 2 * 0.1 plus 10 million. Cost is about $1.54 millions cost of coils with $89 millions cost of generators to generate 23.8 gigawatt. Total cost is about $95 million to generate 23.8 gigawatt, enough for 17 million homes and 95 million people. But when generators are removed and another way used to take energy directly from system, then cost will be $1.5 million for coils only with extra cost to magnets. But when generators are removed and another way used to take energy directly from system, then cost will be $1.5 million for coils only with extra cost to magnets. We observed that the cost ranges from $95 million to $154 million to produce 23.8 gigawatts to 63 gigawatts of power. This cost can be reduced by using different energy extraction technologies. Eliminating steam generators can lower the cost to $1.5 million or less, while still producing very high power. Speed control and generator movement can also be controlled. A faster system can produce very high power. When trains are regulated to be equidistant from each other along a specific track, and the output power from each coil is equal, the coils can be connected in parallel, allowing for direct power generation. This eliminates the need for steam generators, reducing the cost to $1.5 million per 23.8 gigawatts. There are many ways to extract power from the generator, including using a control system to keep the carriages or trains relatively close together. This will produce power at a single voltage. All the coils can be connected in parallel to transmit power directly to the consumer. However, at high frequencies, the consumer installs a capacitor and a switch to convert the high frequencies to DC power stored in the capacitor. The switch then converts the DC power to alternating current, AC. This system reduces the generator cost to less than $10 million. Energy can also be stored from each coil on two capacitors. One capacitor is charged, and when it is full, it charges another. Other capacitors connected to separate coils are also charged. These capacitors, charged with different energies, are distributed equally by being connected in parallel. When the capacitors have the same energies, a switch takes the energy from them, converting the DC power from the parallel capacitors to AC power, which is then transmitted to the consumer. The same process applies to other capacitors that charge from the coils. This is another way to extract power from the generator. The coils can also be connected in series, reducing the number of turns and increasing the diameter of each wire. This allows the system to have a single source or multiple sources with a specific voltage and high current. Absolutely. As you can see, there are many ways to extract energy, such as using a capacitor, a central heating system, and a steam generator. Alternatively, the trains can be synchronized to produce equal power from all the coils. The coils are then connected together and the power is transferred directly to the user. It's worth noting that the first train in this system can be used as a train pulling magnet carrying wheels. It's equipped with a motor and an external power source, similar to an electric train. It's also equipped with a control system to maintain a constant speed and a uniform distance between the trains. These control systems can be quite simple, relying on an inexpensive electrical sensor and a switch to control the electric motor. The switch itself might cost no more than $1, making the control system very simple and inexpensive. Theoretically, a track could be built 63 meters high and very long, extending around the Earth and returning to its starting point. The train would then ascend back to the beginning of the track, and when traveling at high speed, it would generate a very high amount of energy, repeating the process. While theoretically possible, practically, friction and other factors must be considered when using such long lengths at very low heights. Theoretically, at a height approaching zero, an object could be accelerated to a speed of 63 meters per second and travel for a time approaching infinity along a track of similarly infinity length. While theoretically possible, practically, friction between the object and the track, as well as other factors that might limit the maximum speed at which continuous motion can be produced, must be taken into account. An object floating on a magnetic field, a vacuum way, and other such systems could be used to produce motion at great lengths and low heights, accelerating to any speed. However, these systems are more complex. Not impossible to achieve. This system can also be used as a means of transportation between cities, consuming little energy by using a relatively low elevation and a relatively long inclined track. This system can be repeated multiple times along the track. For example, at a height of 63 meters and a length of 6.3 kilometers to 63 kilometers, this system can be repeated 10 times. A certain amount of energy is expended, representing the car and passengers, to lift them to a height of 63 meters 10 times, transporting them a distance of 63 kilometers 10 times, or 630 kilometers, with relatively little energy consumption compared to the track length. This technology is for generating and amplifying energy, and it is the first energy amplification technology in the world in this way. It consumes relatively low energy, which can reach up to 3,200 watts, while producing very high energy over a very long period. The amplification system and its amplification factor are controlled by increasing the track length and increasing the initial speed. The energy produced in terms of time is greater if the track length is 10 times or 100 times longer. From the initial path, and the resulting energy can be increased 10 to 100 to 1,000 times by increasing the speed 10 to 100 to 1,000 times more. Thus, this is a system for amplifying energy and a system for producing clean, continuous electrical energy. It's worth noting that the first train in this series can be used as a locomotive, pulling magnet-bearing wheels. It's equipped with a motor and an external power source, similar to an electric train, and is fitted with a control system to maintain a constant speed and a uniform distance between trains. These control systems are often simple, relying on an inexpensive electrical sensor and a switch to control the electric motor. The switch itself might cost no more than $1, making the control system very simple and cost-effective. The energy output can be increased 10 to 100 to 1,000 times by increasing the speed by a factor of 10 to 1,000. It can be noted that elevators can be replaced by an inclined track at the beginning of the path that rises at an angle of 63 degrees, where a relatively long distance is left at the end of the path, and this path is inclined in an arc, where this arc ends at a distance before the beginning of the second opposite path, and at a certain point it rises at an angle of 63 degrees so that the straight ascending path ends at the beginning of the second path. The same shape is left at a relatively long distance after the end of the second path, through which the path is inclined in an arc that ends at a point that is behind the beginning of the first path, and from that point the path rises in a straight line at an angle of 63 degrees to the beginning of the first path. In this case, the train has moved from the first path and finished the first path and turned. Then the train does not have to turn at a sharp angle which may hinder its movement due to its instability, and it moves in a smooth way without any hindrance that affects its stability in movement and affects energy production.